Hey everybody, how you doing? We're going to be going over some exam review today. We're going to be talking all about one-way and factorial ANOVA. So let's jump into some data right off the bat. It looks like what we're dealing with is we've got 12 different participants, and those participants are grouped into, it looks like three different kinds of majors. Potentially, we got business majors, psychology majors, and biology majors. And then we've got another variable that's categorical, asking whether these students are also work somewhere, right? Like they're employees at some kind of business. And so a couple of the business students are employed and a couple are not. A couple of the psych students are, and some are not. And a couple of the biology students are, and a couple are not. And then we've got a single continuous dependent variable in outcome, which is hours of sleep. So I could ask you a couple different kinds of questions with these types of data, right? If I was just interested in students who work, so who are employees versus students who are not employees, and whether they differ in terms of their hours of sleep, what kind of test would that be? That'd be an independent samples t-test, right? Because you really only have two different groups, two different levels of this independent variable. You're either a student who also works or you're a student who does not also work. Okay. And we're just interested in seeing if sleep on average differs between people who work and people who don't. Okay. If I was to ask you, I think that if I have a hypothesis that I think that psychology majors get the least amount of sleep between all three of these majors, what kind of test would that be? That would be a one-way ANOVA because I'm just interested in one independent variable. That independent variable should have any number of levels greater than two, essentially. And here it has three, business, psychology, and biology. And you're interested again in some kind of continuous or numeric dependent variable. Now, if I were to ask you something like, I think that psychology majors who are also employees get the least amount of sleep compared to any other group, then you're talking about factorial ANOVA. Specifically, it's a two-way ANOVA because I'll have two independent variables. They can have any number of levels, and I'm interested again in just a single numeric outcome or dependent variable. All right, so we're going to go through and actually work through some of these types of things. You already know how to do independent samples t-tests, so I'm not going to run through that. Let's do a one-way ANOVA using major, and we're going to be looking at if there are differences in average amounts of sleep between business majors, psychology majors, and biology majors. So let's take a peek. Again, the first thing that you need to do, you're going to create a model, and that model can be called whatever you want. I'm just going to call it a one-way for now. But again, you could name it sleep one, sleep two, Billy, whatever. You can name it whatever you want. All right, so I'm going to name it one way, and I'm going to use the function AOV, put in some parentheses. You always specify your dependent variable first. And so unfortunately, the data set is named exam underscore three underscore review underscore part underscore one. That's unfortunate. So we're going to hope that this autofills for us. If I type in the word exam, thankfully it autofills or brings up this thing right here that says, hey, this is a data set that you could use. That is the data set that I want to use. I'm going to specify the particular dependent variable by putting in a dollar sign and then sleep afterwards. Okay. I'm going to now put a tilde, and now I'm going to specify the independent variable. So again, I type in exam, that's the data frame, specify the independent variable, which we're interested in major. Okay. And for a one-way ANOVA, bink, that's all I need to do. You'll notice that one way came up into the global environment. To get it out, to actually run the test, you just type in summary and then one way. And boom, here we go. So this shows us that it's testing the independent variable of major and the outcome, although it's not shown on here is sleep because we asked it to do that. And here's the p-value right here, the p-value for this test, for this, what we would call an omnibus ANOVA, meaning like just a general overall ANOVA. This is the p-value, 0.757. So what do you do with the null hypothesis? You fail to reject, right? By the way, the null hypothesis in a one-way ANOVA is that none of the groups, meaning business majors, psychology majors, and biology majors, none of those groups score significantly differently on average in terms of their sleep. Well, let's and so unfortunately, yeah, like we failed to reject for sure. This p-value is above zero point zero 0.05, so we failed to reject. And if we wanted to, we could still take a look at the means, and for some giggles, we can actually try to do follow-up tests, meaning post hoc like Tukey's, or we could try to do a Bonferroni just to get into the habit of that. But when you run a one-way ANOVA, if the omnibus ANOVA is not significant, you just stop, you're done, right? But if we wanted to check out what the actual average sleep is for each of the different groups, you can put tapply in, then you're going to specify your dependent variable, which is sleep. You hit comma, specify your independent variable, which is major, comma, and type in the word mean and hit enter. And you can see that biology majors sleep on average for 7 hours, let's say last night. Business majors, 6 hours last night, and psychology majors, 5.75 hours last night. And none of those are going to be statistically significantly different from each other. We know that none of them are because the overall omnibus ANOVA was not significant. But let's just pretend, we're just pretending that this is actually like 0.007 and that it is statistically significant. Well, even if the omnibus test is significant, it doesn't tell you exactly which of these majors are significantly different from each other in terms of their average sleep. So you would want to conduct follow-up tests. You can do that in two ways. You can either do Tukey HSD, which is a lot easier because then you just put in the name of your model, hit enter, and boom, it would show you all of the possible pairwise comparisons between business majors and biology majors, psychology majors and biology majors, psychology majors and business majors. Do they score significantly differently in terms of their average sleep? And what this is doing essentially is performing three different, basically independent samples t-tests. These are just pairwise comparisons of two levels of the independent variable and one dependent numeric variable. That's just a bunch of independent samples t-tests. And you can see, of course, all of these p-values are not statistically significant. Why? Well, because the overall omnibus was also not significant. But anyways, if it was, you'd have to go check on which specific means were different from the other ones. And so maybe it turns out that like psychology majors do in fact have a significantly different amount of hours compared to biology majors. If this p-value is less than 0.05, you'd go up and you'd say, well, do psychology majors have less or more hours of sleep than biology majors? And if that was statistically significantly different, then you could actually, state that. Of course, in this case, it's all made up, and no, there's no significant differences. You could do a different type of follow-up test, which is called the Bonferroni. You should know both ways for the exam, just in case I ask you one or the other. In that case, you're going to do pairwise.t.test. You're going to specify the dependent variable, which is sleep. Then you comma, specify the independent variable, which is major. Then you do another comma and you have to type in, let's see, p.adjust.method equals, add some quotes, lowercase, Bonferroni. Okay. Okay. So this looks a little funky, but these would be the p-values. One is as high as it goes. That's going to be, like that that's as high as it possibly can go. That means there's 100% likelihood that you would see an F value, even though we don't actually know what the F value is here. there's a 100% likelihood that you would see such an F value if, in fact, the null hypothesis was correct. And so you can't reject the null hypothesis. If the p-value is less than 0.05, then you can reject the null. But if it's 1, there's no way. Okay. You can see just in terms of these differences, like why did the Tukey's p-value, why are the Tukey's p-values a little less than 1, meaning they're less than the Bonferroni p-values? Well, remember, Bonferroni is a more conservative test, and what that means is it makes it more difficult to actually reach significance, which sounds bad, but at the same time, it means it's also less likely to commit a type 1 error. So people like it using Bonferroni's, but I've seen a lot of people use Tukey's as well. Okay, so that would be a one-way ANOVA. Again, if the overall omnibus F test is not significant, you just stop. You're just done. It means that none of those means are statistically significantly different from each other, and you fail to reject the null. But if it is significant, if the overall omnibus test is significant, it means you have to do follow-up tests because you have to figure out exactly which means are different from each other. All right. Now, that was a one-way ANOVA. Let's try the factorial ANOVA, the factorial ANOVA. Let's say, again, I think that specifically the people who are psychology majors and are working get the least amount of sleep. Okay, so that's involving both of these independent variables as well as the single dependent variable. So I'm going to create a new model. I'm just going to call this one sleep one. You could call it two-way. You could call it, whatever. You can call it your best friend's name or your pet's name or something like that. But anyways, sleep one. Again, we're using the AOV function. This time, you have a little bit more work to do. You're going to specify your dependent variable, which again is sleep. But this time, you're doing tilde, specify the first independent variable, which will again be major. But now you hit plus, and you specify the second independent variable, which will be employee. And now you have to hit plus again. And you kind of do the same thing. You're going to specify the first independent variable, which is major. And now you do colon and specify the second. Oh no, it's not going to autofill for me. So I'm going to have to write this whole thing out. Exam underscore 3 underscore review underscore part underscore 1. That's fun. Okay. All right. So that's the model. This is a lot, right? So we're talking about analysis of variance. We specify sleep as the dependent variable. We put in our first independent variable, which is major. Then we plus our second independent variable, which is employee. Then we plus, and now we have to do the interaction term. The interaction between major and employee. So that's what this colon is doing. It's saying, give me an interaction term of major by, major by employee. All right. Going to hit enter. Nothing's going to happen except for you see sleep one got put up in the global environment. That's good. Then we type in summary, and I'm going to type in sleep one. Boom. Okay, here we go. So what just happened? In a factorial ANOVA, specifically a two-way ANOVA, you have three different tests that you just had R run all at the same time. You're running three different tests, okay? The first row is the main effect of major. The main effect of major, okay? Well, guess what? What is the main effect of major? The main effect of major is a one-way analysis of variance. We already did that, right? Like we know that's not going to be significant. So basically, it just performed another one-way analysis of variance on major, trying to see if there's different amounts of sleep between the major. P-value is not significant. So, okay, you don't have to go like do anything more specific for that. You don't have to do any follow-up tests specifically for the main effects of major. How about the main effects of employee? That's just an independent samples t-test, essentially asking if people who are employees sleep a different amount of time than people who are not employees. Is that significant? Yes, it is. It is significant. 0.28 times 10 to the negative fifth means an 8 with four zeros in front of it. Okay, so that's a very small number and it's less than 0.05. So that is statistically significant. That means that there's a significant main effect of employee. In what direction, though? We don't know if employees or people who are not employees sleep more or sleep less. And so you would do a T apply, and you're going to specify your dependent variable, which is sleep, comma, your independent variable, in this case is employee, hit mean, and there we go. People who are not employees sleep 8 hours on average, and people who are employees sleep 4.5 hours on average. We know that those two numbers are statistically significantly different from each other. You don't have to do any like follow-up post hoc tests because there's only two means. So they are automatically going to be different from each other. If there were more than two means, meaning more than two levels, more than two groups, you would have to do like a Tukey or you'd have to do a Bonferroni. But because there's only two groups, we know that those are statistically significantly different from each other, such that people who don't work sleep more on average than people who do work. That makes some sense. All right, how about the interaction term? Is the interaction term or the test for interaction significant? Yes, it is. 0.003 essentially. Okay, p-values get rounded to three decimals, typically speaking, so 0.003 is less than 0.05. That means that there is a significant interaction. Okay, well, how are we going to figure out like which group was let's say sleeps the least? Well, first of all, I'm going to ask you, what kind of design is this? If major has three levels and employee has two levels, what kind of design is this ANOVA? It's a 3 by 2, right? It's a three levels by two levels kind of design. And so how many cells, how many unique groups are we going to expect between business majors, psych majors, biology majors, employees, and non-employees? Well, you just multiply 3 by 2. You should get 6 unique averages for those 6 different groups. Business people, excuse me, business majors who work, business majors who don't work, psych majors who work, psych majors who don't, biology majors who do, biology majors who don't. Okay, so we're going to do T apply again, but in this case, it's going to look slightly different. Specify the dependent variable. Now you actually write out the word interaction and put in a new set of parentheses. Specify the first independent variable, comma, the second independent variable, which is employee. Then outside of the first set of parentheses, but inside of the second set of parentheses, you type in comma, mean, boom. All right. Do we have 6 averages? Yes, we do. And that's a good thing. So this is saying again, for people who are biology majors but don't work, they sleep on average 8.5 hours. Business majors who don't work, 6.5 hours, and so on. Now, how do we know which of these are statistically significantly different from each other? And we know that at least 2 of them will be different because this interaction term is significant, but we don't know which ones yet. So that's why we're going to have to do some follow-up testing. Again, you could use Tukey or Bonferroni. Let's do it both ways. Tukey, in this case, we're using sleep 1. Boom. It's going to give us all kinds of comparisons, all kinds of possible comparisons. Um, and, and you can see which ones are statistically significant or not by the p-value. You are not interested in this diff, lower and upper stuff, just the p-values. Okay. So this is a lot, but it's trying to test every possible pairwise comparison between those 6 different means, and there's a lot of possible combinations. And so on the exam, I could just ask you, well, which of those turned out to be statistically significant? And you could hunt through all of these and say which ones are, or if I ask you which ones are not, then you'd hunt through them all and say which ones are not. Let's just kind of take an eyeball guess at this. It looks like psychology majors who also work they're probably going to be statistically significantly different than all these other ones. Let's go see. Our psychology majors who also work. So anytime you see psych yes, is there a, yeah, that's a significant p-value. Psych yes, significant p-value. Psych yes, significant p-value. This one's both of these on the bottom are psych yes and significant p-values. Okay, so anytime you say the group that are psychology majors and also work, they do have a statistically significant difference from basically every other possible mean. And therefore, you can see that that is statistically significantly the least amount of hours slept. But you'd want to also double check and see if there are other significant differences, even between groups that don't involve psych. Like, for instance, this one right here. This is just the difference between people who are biology majors who work versus biology majors who don't work. So that's biology no versus biology yes. That's a statistically significant difference as well. So you just want to look through and answer based on what the exam is going to ask you. Okay. Another way you could do it is with the Bonferroni method. That's again pairwise dot t dot test. You're going to specify your dependent variable, comma, you have to write out interaction, new set of parentheses, specify the first independent variable, comma, the second independent variable, and then now you do, comma, p dot adjust method, and quote spawn for, let's see it. Yep. Okay, and it's going to give you, generally speaking, it'll give you the same results. Even in fact, this kind of looks a little bit nicer. This would say this is a p-value for the test of business no versus biology no. You see that? This is psych and not employees versus biology and not employees. And that's one. Okay, so um, yeah, hopefully that was interesting. I've got one more thing that I want you to do. So not only be able to do, actually conduct via R the one-way ANOVA and two-way ANOVA and follow-up testing and knowing, which means are statistically significantly different and all that good stuff. But also, I might throw you something a little tricky like this on the exam, where I will give you some output, okay? I'll give you some output for maybe a factorial ANOVA or maybe just a one-way ANOVA, but I'll have some missing numbers in there, and I'll ask you to actually fill some of these things in. And let's just walk through some of these questions that I've got here. Okay, how many main effects are you testing in this output? All right. Well, it looks like we're testing the main effect of music, the main effect of car, and then there's an interaction between music and car. And then the residuals is that's going to be for all the within groups type stuff. So we'll get to that in a second. So whenever you have a factorial ANOVA and there's two independent variables, then you're going to have two main effects. So how many main effects are you testing? Two. Which of the main effects are significant? Oops, this is supposed to say music, and this is supposed to say music. Okay, the main effect of music, is that statistically significant? Yes, it is. Yes, it is. 0.0004 is less than 0.05. The main effect of car, 1.8 times 10 to the negative fifth. Yes, that's less than 0.05. The interaction between music and car, yes, again, 0.0015 is less than 0.05. So those, all three of these effects, the two main effects and the interaction term, all of those tests were significant. What is the mean squares between for music? Okay, so that's asking about this blank right here. What is that number? All right. Well, to find mean squares between, you have to divide sums of squares between by degrees of freedom between. Okay, sums of squares between by degrees of freedom between. So let's go back. So that would be sums of squares between, which is this number right here for music, 425.6. And then degrees of freedom between is right here, is 2. So you divide 425 0.6 by 2, and I got 212.8. Okay, 212.8. What is the F value for the effect of music? What is the F value? Okay, the F value, now you're going to take the between groups variance, which is also known as the mean squares between, and you divide it by the within groups variance, which is also called mean squares within. So you're going to take mean squares between for music divided by the mean squares within. Well, where do we find those numbers? Well, you just calculated the mean squares between. The mean squares within for all of these tests, the music, car, and music by car, mean squares within for all of those is this number in the residuals. Mean squares within is 12.8, so I already gave you that. So you would do that number that we found before, 212.8 divided by 12.8. And that should get you, if I did my math right, 16.63 as the F value. Okay, so then that would go right here. That would go right there. Okay. How many levels of each independent variable are there? How many levels? All right. Let's say, how many levels are there for music? Well, we can see that the degrees of freedom are 2. That's not quite the number of levels, though. We can see here the degrees of freedom between for the first variable, let's call it A, are the number of levels of that variable A minus 1. So if the degrees of freedom between for music is 2, what is the number minus 1 that equals 2? Well, it's 3, right? 3 minus 1 equals 2. So we know that if the degrees of freedom is 2, one more than that is going to give you the number of levels, which is 3. So music has 3 levels. What about car? Well, car, we can see there's degrees of freedom of 1. Car, we can see degrees of freedom of 1. We go back here. Well, it's the exact same story, okay? The degrees of freedom between for the second variable is the same thing. It's the number of levels of that variable minus 1. So if the degrees of freedom between it is 1, what's a number that, if you subtract 1 from it, equals 1? Well, that's 2. So you know that there's only 2 levels for car. By the way, what are we testing? The dependent variable is number of speeding tickets. So I'm guessing that there's going to be 3 different levels of music, something like metal, let's say rap, and let's say country or something like that. And car could be like the type of car. And if there's only 2 levels, we could be talking about like sports car versus other cars, or I don't know, 4-door cars versus 2-door cars, or something like that. Okay. How many people are in this sample? Now that is a trickier question. How many people, just based on this information alone, in fact, just based on this column of information, the degrees of freedom, you can figure out how many people are in this sample. How do you do that? Well, I can see that this number right here is 18. That's the residuals. That means the degrees of freedom within, degrees of freedom within. Okay, how does that help me? The degrees of freedom within is calculated as the number of people in the sample minus k. And for a factorial ANOVA, k is the number of cells. The number of cells. Well, how do we get to the number of cells? Remember, you multiply how many levels are in the first variable times the number of levels in the second variable. We found out there are 3 levels of the first and second and 2 levels of the second. So 3 times 2 would result in 6 cells. 6 would be K. Okay, so if K is 6, what is the number, the total number of people? What is the number that minus 6 gives you the degrees of freedom within of 18? So all you have to do is add 6 to that number, and then you figure out that there's 24 people. 24 people in the sample. All right. So for the exam, you definitely want to know all of the stuff we just covered for this, but also in terms of are you want to know how to conduct a one-way and a two-way ANOVA, including follow-up tests and being able to tell me which of the means are statistically significantly different from each other and maybe what actually are the means for different groups. All right, best of luck. See you in the next one.